This is the fourth video about wind turbines. Before we talk about the actuator disk model for the wind turbine, we need to understand the streamlines and the Bernoulli's equation. The streamline is a quite familiar concept. Even for people who are not familiar with fluid dynamics, the concept of streamline still makes sense. If we would like to describe it in a more concrete way, we can relate it to the concept of a path line, which is the path traced out by a massless particle as it moves with the fluid. For steady flow, which means that properties of the flow do not change with time, path lines and streamlines are identical. So this figure shows some examples of streamlines around an airfoil, and around a cylinder. So those lines here are examples of the streamlines around those two different objects. One important thing to understand is that at every point along the same streamline, so if we actually look at just one streamline, at every point on it, the instantaneous velocity, the local velocity of that particle we are tracing is always tangent to the streamline. So there is no velocity component that's perpendicular to the streamline. Which means if there's no velocity component that's perpendicular to the streamline, which means there's no mass transfer, there is no mass flow across streamlines. So there is no material that actually flows across streamlines. Streamlines actually indicates the direction of mass movement. But across the streamlines, there is no mass movement. So if we actually pick two arbitrary streamlines, for example, if we pick this one and pick this one, because there's no mass flow across the streamlines, so between these two picked streamlines, the mass flow is constant. There's no mass that's actually going across these two boundary streamlines. That's in two-dimensional space. If we consider three-dimensional space, if we consider flow in a three-dimensional space, then we can come up with the concept of a stream tube with its boundary defined by a collection of streamlines. In this case, all those blue lines are actually streamlines that's located on the boundary of the stream tube. Again, the velocity of the particle that we're tracing is always tangent to those streamlines. So there is no mass flow that's across the boundary of this particular stream tube. So if we consider a stream tube, then the mass flow within this tube is always constant. And later on, when we talk about the actuator disk model of wind turbines, we will use the concept of a stream tube. Now, once we have some basic concept about the streamline, let's consider such a cubic fluid particle, a very, very small cubic fluid particle that's located on this streamline, that's actually flows along this particular streamline. This cubic fluid particle has a surface area of capital A. So the surface area in this direction is capital A. And it's got a length. We're going to denote the length as L. For some reason, the L is kind of not so clear, right? But the length here is L, right? Length here is L. And then we're going to assume that the pressure behind the particle is small p, and the pressure in front of the particle is p plus dp, and the particle is actually moving with a velocity that's v in the direction of the streamline. Right. The purpose of our analysis is to find out some kind of relation between the pressure p and the velocity v. Right. So if there is this kind of pressure difference on the back and on the front of the particle, then this kind of pressure difference is going to generate a net force that's acting upon this particle. Because pressure is just a force times area, right? So if you have a pressure difference on the front and on the back of this cubic particle, then you must have a net force, right? You must have a net force. And according to Newton's second law, force equals to mass times acceleration. So this net force is going to create a acceleration, right? And then we can write it down like that. So express the acceleration as the time derivative of the velocity v. So F equals to m dv dt. Right. So now let's try to find out an expression for the F first. What's going to be an expression for F in terms of P, right? So because pressure is just the force divided by area, right? So force is pretty much just the pressure multiplied with the area, right? So on the back of the surface, pressure is P, the area is A, right? And on the front of the surface, pressure is P plus dP, and the cross-sectional area is A, right? So the net force difference, the net force is just going to be A multiplied with dP. The minus sign indicates that this net force is actually in the direction of the negative x, actually goes against the x direction. It goes this way. Right? So F equals to minus dP multiply the cross-sectional area, big A. Right? Then what exactly is dP, right? What exactly is dP? What exactly is dP? Right. dP is the pressure difference across the length of this particular fluid particle. And the length of the fluid particle is L. It's L here, right? So dP is equal to what? dP equals to dP over dx. That's the that's the derivative of the pressure along the x direction, which indicates the rate of change of the pressure along the x direction. It indicates how fast pressure actually changes along the x direction. Right? If we multiply the rate of change with the distance along the x direction, which is L, then we get dP. So dP actually equals to the rate of change, dP over dx, multiply the length of the particle, which is L. Right? So that gives us an expression for dP. And then we can actually bring this expression of dP back in this equation. F equals to minus dP times A, right? Then what we are gonna get is a new expression for F, the net force. The net force is gonna equal to minus, replace dP with L, dP over dx, and then multiply A. So if we bring the expression of F back into the second law of the second Newton's law, then it's minus L dP over dx, L dP over dx multiply A. The minus sign here, right? Right. So the left-hand side of F equals to ma becomes this thing. So F equals to minus L dP over dx times A, right? It's still going to be equal to m times acceleration, right? Acceleration is dv over dt now, right? And then what's going to be the mass of the fluid particle, right? The mass of the fluid particle is going to be equal to the density multiplied with the volume of the particle. Let's assume the density is just a rho, right? The density of the fluid is just a rho. And then what's going to be the volume, right? The volume, we know the surface area, the cross-sectional area of the particle is big A, right? We know the length is L, so the volume is A times L. A times L, right? So now we got a new expression for the Newton's second law for this particular fluid particle along the streamline. Right? And this particular expression can be rearranged and simplified. Right? But now let's try to find out the relation between dp and velocity, p and velocity. We're going to use this result later on, but now let's try to actually find out the relation between p and v. So on this particular equation, L and L cancels out. A cancels out. So the left-hand side becomes minus dp over dx times unity, right? Because A has cancelled out. Equals to, A has cancelled out, L has cancelled out, rho dv over dt. So it's minus dp over dx equals to rho dv over dt, right? And then you can multiply the dx on both sides, right? So what you are getting is dp equals to dv over dx multiplied dx times rho, right? So that's exactly what we are having here. So dp, right? dx has been multiplied over on both sides. So dx cancels out. So it becomes minus rho dv over dt times dx, right? So this particular equation is basically this particular equation after some algebraic manipulations. Basically just cancels out LA on both sides, multiply minus 1 on both sides, and then multiply dx on both sides. Then we get this particular equation, right? And then dx over dt is what? X is actually the direction, x is actually the distance the particle is actually moving along this particular direction, right? So dx over dt actually gives you the velocity of the particle, right? It's exactly the v, the velocity of the particle v. So if we replace dx over dt here with v, we have obtained dp equals to minus rho v, dx over dt is v, right? And then dv. That's the expression between pressure and velocity, right? And the dp, changing pressure and changing velocity, right? Changing velocity, pressure and changing velocity. And this particular equation can then be integrated between two arbitrary points on the same streamline. So if we actually pick any two points on the same streamline, suppose point 1 and point 2, for example, point 1 here, point 2 here, or point 1 here, point 2 here, any two arbitrary locations, right? So we do an integration. We do an integration between these two arbitrary points, 1 and 2, right? So the left-hand side becomes P2 subtract P1. And then let's assume density doesn't change along the streamline, so density is a constant, right? So we can take the density out of the integral, right? And then it's just a v, dv, goes from like 1 to 2. And this integral can be calculated quite easily, right? So v dv is just the v squared divided by 2, right? The integral of v dv is just the v squared divided by 2. And because it's between point 1 and point 2, so it's rho times v2 squared divided by 2, subtract rho times v1 squared divided by 2, right? So we obtain this equation between these two arbitrary points. And then the next thing we have to do is to actually just rearrange this particular equation. We collect all the terms that's related to position 1, and then we collect all the terms related to position 2, right? So P1 plus rho v1 squared divided by 2, right? P1 plus rho divided by 2 v1 squared must equal to P2 plus rho divided by 2 v2 squared. Right? And because these 2 points, 1 and 2, these two locations are arbitrary, which means this particular equation, this particular constant, this particular quantity must be a constant, must be a constant along the same streamline, right? Because point 1 and point 2, position 1 and position 2 are two arbitrary positions, right? And this is actually the Bernoulli's equation. This is the Bernoulli's equation. It's a relation between pressure and velocity at different locations on the same streamline. It basically states that pressure plus density divided by 2 times the velocity of the fluid squared is a constant along the same streamline. In practice, on this particular figure, the streamline, the dashed line, is a straight line, right? But in practice, the streamline can be curved. It could be curved. It has some curvature to it. It can bend in different ways, right? But it doesn't matter. The same analysis still applies because we can always create a local coordinate system, right? For every position of the particle along the streamline, we can create a local coordinate system with its x direction that's lying in the direction of the local velocity that's tangent to the local streamline. Right? So the same analysis still applies, and the result is still correct for curved streamlines. If we translate the Bernoulli's equation into plain English, we obtain Bernoulli's principle, which states that along the same streamline, higher pressure regions have lower fluid speed, and lower pressure regions have higher fluid speed. The reason is because pressure plus speed squared times rho divided by 2 is a constant. So if pressure is big, then this one must be small, right? Which means V must be small. Right? And if V is big, then pressure must be small. Right? If pressure is pressure and plus this quantity must be a constant. So that's what Bernoulli's principle actually means in plain English. And there is also a different perspective for understanding the Bernoulli's equation, which is based on the conservation of mechanical energy. We are probably familiar with kinetic energy and potential energy, but may not be familiar with the pressure energy. In fact, pressure can be considered as the density of the pressure energy. In the simplest form, pressure is just equals to force divided by area. If we multiply both the numerator and the denominator by the distance over which the force has acted upon, so we multiply both the numerator and the denominator by the distance d. Right? F times d, it's force times the distance the force has acted upon, which actually gives you the work this force has done. Here we represent it as W. And A is the area, right? A is the area the force is acting upon, times D actually equals to the changing volume of the fluid, right? Area times distance, that's a volume. Right? So basically, work has the unit of energy. V is volume, so it's basically energy divided by volume. That's exactly the volume density of energy. So if you think about it, pressure actually causes some kind of energy which we call a pressure energy. And the pressure itself is the density of that particular energy. It's a volume density of that pressure energy. Right? For kinetic energy, the form is more familiar to us, right? It's 1/2 mv squared. V is the speed of the fluid particle. Right? M is the mass of the fluid particle. So m divided by volume, that gives us the density of the fluid. So it's 1/2 density v squared. So that's the kinetic energy density, fluid kinetic energy density. Again, a volume density, right? It's a volume density of the kinetic energy. And then we can also consider a fluid potential density energy, which is basically just the potential energy divided by volume. Right? Suppose the fluid is flowing in the gravitational force in the gravitational field of the Earth, right? Then the potential energy is mass times the gravitational constant times the height of the fluid particle. Again, we want to get the volume density of it, so we divide by V, right? So mass divided by V equals to the density of the fluid, so it's rho gh, right? So because if we do not consider any other kind of energy, then the mechanical energy should be conserved, should be conserved along the same streamline, right? And all the mechanical energy just so at every point the mechanical energy is just the summation of the pressure energy, the kinetic energy, and the potential energy, right? And if we consider the density, the energy densities, then it's just the P plus 1/2 rho V squared plus rho G H, right? So if we pick just the two arbitrary locations, location 1 and location 2, then we get these two. Then the mechanical energy for position 1, that's the summation of these three terms, must equal to mechanical energy at position 2. Right. So this equation is basically identical to the equation in the previous slide here, right? With only just the one slight difference, which is the potential energy here, right? But the potential energy can usually be ignored if we just consider, if we compare the potential energy with the other two forms of energy. It's much smaller than the other two, energy types. And another case that we can ignore potential energy is when the streamline is more or less at the same height, right? The two positions on the same streamline, H1 and H2, the height is about the same at these two positions. And in that case, rho gh1 and rho gh2 cancels out because h1 almost equals to h2, right? And in both cases, we can ignore the potential energy. If we combine the Bernoulli's equation with the so-called continuity equation, we can obtain a relation between cross-sectional area of the flow and the pressure. So the continuity equation is a consequence of conservation of mass in a fluid. So the total mass of fluid, the total amount of mass of the fluid that's flowing into this particular pipe must equal to the total amount of mass that's flowing out of it, right? And what exactly is the total amount of mass that's flowing into it, right? The mass equals to density times volume, right? So suppose density of the fluid coming in is rho 1. And then what's going to be the volume, right? The volume is going to be the cross-sectional area, let's say A1, times a distance the fluid has flown through. So if we consider just a unit time interval, the time interval that we're considering is just 1, right? Then the distance the fluid has flown through is going to be equal to the speed of the flow. That's called V1, right? Times the unit time, times 1, right? That's the distance, right? So the volume is just going to be the cross-sectional area A1 times V1 times 1, right? That's the volume. So that's multiply the mass rho 1, multiply the density rho 1, then we get the total amount of mass that's actually flowing into this particular interface, right? And then we can apply the same analysis for this end, right? Suppose the density coming out is rho 2, the cross-sectional area is A2, and then the flow speed is V2, right? If we assume that the density doesn't change, usually the density doesn't actually change. So rho 1 equals to rho 2, so we can cancel out rho on both sides of the equation, and then we get the so-called continuity equation. That's the cross-sectional area A1 times V1 must equal to cross-sectional area A2 times V2, right? And because A1 is bigger, right, is bigger than A2, this is a much bigger cross-sectional area than this one. So V1 must be smaller than V2, right? So the speed of the fluid that flows into it must be smaller than the velocity of the fluid that's coming out. Right? So this is actually consistent with our experiences. If you actually use a garden hose to irrigate your lawn, right? And if you actually put a thumb at the outlet, put your thumb on the outlet of the pipe, then the speed of the water that's coming out of it, out of the pipe, is going to be much faster, right, than before, because you have reduced the cross-sectional area of the outlet, right? So because A1 is larger than A2, so V1 is smaller than V2, right? And then according to the Bernoulli's principle, if V1 is smaller than V2, then pressure at location 1 must be larger than the pressure at location 2. So we have P1 larger than P2, right? So if we know the cross-sectional area, if we know the relation between the cross-sectional area, we can derive a relation between the pressure at these two locations. And that's Bernoulli's equation and Bernoulli's principle.